Welcome to this explainer. Today, we're unpacking something pretty wild. We're going to look at how invisible forces from the sun can reach across millions of miles and completely disrupt the precise positioning systems we rely on every single day. Let's start with this everyday illusion of certainty. Think about it. You're following a static blue dot on your phone to navigate a busy city. Or maybe you're watching a massive tractor perfectly map a field down to the centimeter. Or even a drone just effortlessly holding its position against the wind. It feels locked in, right? Permanent. Perfectly reliable.
But here's the crucial question driving our whole explainer today. How can the sun literally move that blue dot, even when all the satellites orbiting 16,000 miles above us are functioning absolutely perfectly?
To really get at this system beneath all this, we first need to establish our baseline by tracing a healthy signal from space all the way down to Earth.
Now, your device doesn't just inherently know where it is out of nowhere. There's a whole causal chain of events here. A satellite beams a highly precise time message. Then your receiver measures the exact travel time of that signal to calculate the distance, or the range, to that satellite. If you measure the range from 4 or more of these satellites, that single intersecting measurement dictates your exact location. But, that all assumes a pristine pathway from orbit straight down to your antenna.
And of course, the anatomy of a space storm tells us that this pristine pathway is highly vulnerable. Let's introduce the cosmic actors that can actually break our baseline.
We need to clearly distinguish between the levels at play here. First off, you have solar flares. These are intense bursts of radiation moving literally at the speed of light. They hit Earth almost immediately, ionizing the atmosphere and causing radio blackouts, mostly on the day side of the planet. But then you have coronal mass ejections, or CMEs. A CME is a directional stream of plasma. We're talking 1 billion tons of matter ejected right from the solar corona. And when an Earth-directed CME slams into our planet's magnetic field, well, that triggers a full-blown geomagnetic storm.
Which leads to our third level, the ionospheric response, creating a bias that literally bends the signal. This is our first major failure mechanism when those geomagnetic storms hit the upper atmosphere.
So, the big takeaway here is that geomagnetic storms drastically increase something known as the total electron content, or TEC, in the ionosphere. As the GPS radio signal passes through this highly charged plasma, its path is physically bent. It's slowed down. It acts exactly like a giant lens bending a beam of light. Keep coming back to one fundamental question. What did the receiver actually think the signal travel time meant? Because your phone, or that tractor, it assumed a normal, quote-unquote, quiet ionosphere, and it used a standard mathematical model to correct for atmospheric delay. So when the TEC suddenly surges, that model utterly fails. The math becomes biased. The delay gets interpreted as extra distance, and suddenly, single-frequency positioning accuracy can plummet from a single meter down to tens of meters.
And there's a great research case study that brilliantly illustrates this real-world impact. Take the historic G5 geomagnetic storm from May 10th and 11th, 2024. During that active solar peak, researchers documented that high-precision real-time kinematic networks, which is exactly the kind used in advanced agriculture, saw significant disruption. The carrier phase ambiguity fixing rates just dropped, and horizontal positioning accuracy degraded severely. So when heavy machinery requires strict centimeter-level precision for planting, this level of bias completely throws off operations.
But it gets worse. Let's look at the sheer chaos of losing the lock. This is our second causal pathway, and it's less about calculating the wrong distance due to a bent signal and more about total system failure.
This brings us to a phenomenon called scintillation. Instead of a uniform lens just bending the signal, geomagnetic and even natural equatorial activity can create small-scale irregularities in the ionosphere. Think of them essentially as plasma bubbles. When the GPS signal passes through these bubbles, it actively gets diffracted and scattered. From the receiver's perspective, the signal goes through rapid, chaotic fluctuations in both phase and amplitude. It literally twinkles, much like a star in the night sky. When observing tracking diagrams covering this phenomenon, you can visually trace how these plasma bubbles primarily form near the Earth's magnetic equator, and they're particularly severe right after sunset. As the satellite beams its signal down, it intersects this turbulent layer, and the signal path gets severely scrambled before it ever even reaches the antenna.
Operations dashboards tracking this over places like South America show exactly what that chaos looks like in real time. You'll see massive spikes in GPS phase noise lighting up in coral and red. And this isn't just a minor delay we're talking about. This severe phase noise pushes the receiver into a high-risk state where it can suffer complete signal power loss,
meaning it loses its lock on the satellite entirely. Now you might be wondering, well, can't we just upgrade our receivers? It's a fair question, and it's true that dual-frequency receivers can cleverly compare two different signal frequencies to calculate and remove those standard ionospheric delays. But under highly disturbed conditions with severe scintillation, even dual-frequency systems are not immune. They can absolutely lose their lock. Plus, it's really important to remember that while severe solar activity definitely increases these bubbles, equatorial scintillation is also just a natural part of the normal day-night cycle. Moving on to the invisible timing network, we have to realize this isn't just a mapping or navigation problem. At its very core, this entire infrastructure relies on exact timing. Remember, receivers calculate distance by measuring the exact arrival time of a signal at predetermined epochs. That's our data sampling rate. So corrupting that travel time essentially corrupts the clock. GPS isn't just for location, guys. It is the invisible global timing network that synchronizes our power grids, our cellular networks, our financial systems, the whole shebang. When the ionosphere shifts that arrival time, it perturbs the actual heartbeat of our modern infrastructure.
Which brings us to designing for resilience. How on earth do we engineer resilience when the space environment itself becomes the bottleneck?
You have to map out a clear decision tree, step by step, because resilience requires knowing exactly how your system is going to fail. If TCE bias kicks in and puts you in a state of reduced confidence, well, dual frequency corrections act as your first fallback. If high scintillation triggers warnings and noise, critical systems need timing holdovers or strict integrity checks. But if the receiver rejects the solution completely due to a loss of lock, critical operators absolutely must have alternate navigation systems ready to go, like the ground-based LoRaN or Omega networks. And right here is a fascinating constraint. We call it the integrity paradox. Modern receivers use something called Receiver Autonomous Integrity Monitoring, or RAIM, to double-check signal reliability. But RAIM operates on one foundational assumption. It assumes the vast majority of the GPS constellation is healthy. Since geomagnetic storms are global influences that perturb the entire ionosphere at once, the whole system degrades together. So RAIM might successfully warn you that your location is failing, sure, but it cannot magically provide a reliable replacement signal.
At the end of the day, we have to preserve a really deep respect for the sheer uncertainty of space weather. We can't just paint with a broad brush here. These disruptions vary wildly. The exact effects depend dynamically on your latitude, the local time of day, the specific engineering of your receiver, the signal frequencies you use, and, of course, the sheer severity of the incoming solar storm.
Ultimately, this explainer leaves us with one critical thought for our hyper-connected infrastructure. As solar maximums peak and our reliance on centimeter-level precision only continues to grow, we have to ask ourselves, when the invisible system beneath our modern world breaks, what is your fallback?